Very good evening, my dear students. Welcome back to the second session of complex variable topic. In the first session, we have seen the four definitions. The first one is the neighborhood of a point. The second one is analytic function at a point. The third one is the singular point. And the fourth one is entire function. We have seen these definitions, and also we have taken some examples also, and also we have seen how to check the function is differentiable at a point, and we have seen how to check the analyticity of a function at a particular point, and also we have done some questions on this, that is some examples on this, and we have seen how to check the analyticity at a particular point, differentiability at a particular point. Now we do the problems on integral of complex function along the closure curves. For the evaluation of integral of complex function along the closure curve, we use the two theorems, the Cauchy's theorem and Cauchy's integral formula. So first we look at the Cauchy's theorem statement of a theorem. The name of the theorem is Cauchy's theorem. The statement is, if a function f of z is analytic at a very point inside and on a simple closure curve C, then integral of the complex function along the closure curve is always 0 only. If you are given some complex function, if you are given the complex function and that function is given that analytic at every point inside the on the closure curve C, then the integral of that function along the closure curve is always 0 only. So this is the first theorem, Cauchy's theorem, right? According to this theorem, if you are given integral of complex function and we check that function is analytic inside C, on C or not, inside C, on C, analytic, then the integral of the function along the closure curve is always 0. That is it. Now here, simple closure curve. We discuss about the simple closure curve and simple curve, right? And also the different types of regions, and then we come back to this only. If you draw a curve like this, and this curve has no self intersection only, the curve is not intersecting itself only. If a curve does not cross itself, then the curve is called simple curve only. It is called simple curve. Suppose the curve crosses itself at one or more points, at one or more points like this. If a curve crosses itself or the curve has self intersection like this at one or more points, then the curve is called multiple curve only. This is multiple curve. And this is simple curve only. The curve is not having any self intersection, or the curve is not intersecting itself only. So it is simple, it is multiple curve only. Suppose if we join the initial point with the terminal point, the starting point with the ending point, then that becomes closed. First of all, the curve is simple as well as closed in such case. Then in such case, the curve is called simple closure curve only. Now the curve is simple and also closed. So this is the simple closed curve only. First of all, it is multiple curve because the curve is crossing itself, or the curve has self intersection only. If we join the initial and terminal point, then the curve becomes closed. This curve is called multiple closure curve, and this is called simple closure curve only. This is simple closed curve, and this is multiple closed curve. Both are closed, but one is simple, other one is multiple. So it is simple as well as closed. It is multiple as well as closed. So multiple closed and simple closed. We always consider like this simple closure curves only for the evaluation of integral of complex function along the curve. Next, we'll discuss about the different types of regions. you draw a simple closed curve C, if you draw a simple closed curve C, this closure curve bounds some plane region only. Inside the closure curve C, we can find some plane region. This region R is called simply connected region only. This is called simply connected region only. The region R obtained by drawing a simple closure curve C is called simply connected region only. That is, inside the closure curve, we are taking the total portion. Then this is called simply connected region only. Inside the simple closure curve C, if you leave some portion only, if you leave some portion like this, C1, that is, we are taking the region only inside C, outside C1, that is between C and C1 only. And this type of region is called multiply connected region only. Multiply connected region. That is, inside the simple closure curve C, if you leave some portion like this, then this is called multiply connected region only. Here the region is between C and C1, interior to C, exterior to C1 only. C, C1, C2, here the region is interior to C, exterior to C1, C2, C3. Here the region is interior to C, exterior to C1, C2 only. Not within C1, not within C2 only. So these type of regions are called multiply connect regions only. So we have two types of regions. One is simply, other one is multiply. This is simply connected region only. Inside the simple closure curve C, inside the simple closure curve C, if we consider total portion, that is simply connected region, and if you leave some portion, inside the simple closure curve C, if you leave some portion, or if you leave some like this portion, then the region is called multiply connected region only. So we have two types of regions. One is simply, other one is multiply only. Now this is the theorem. The name of the theorem is Cauchy's theorem. This theorem is for simply connected region R. Simply connected region R, right? Because we have taken the simple closure curve C, and inside C we are considering total region only. So whenever the function f of z inside the integral is analytic at every point inside C on C, then the integral along the closure curve is always 0 only. This is about Cauchy's theorem. And we extend the same theorem for multiply connected region also. Here we have written the only theorem for simply connected region only. We can extend this same theorem for multiply connected regions also. C, C1, C2 only, or is the region multiply connected region. If a function f of z is analytic at every point inside C, outside C1, C2, not inside C1, not inside C2 only. So in this region R, the function is analytic, then integral along the closure curve C, is equal to integral along C1 f of z dz plus integral over C2 f of z dz only. This is the Cauchy's theorem for multiply connected region only. Suppose the region is like this, C, inside C, C1, C2, C3, or is the region. Now again for this multiply count region, the integral along over along C f of z dz equal to integral along C1 plus integral along C2 plus integral along C3. The integral along this curve C is equal to integral along C1 plus along C2 plus along C3 only. Inside C, if we have any number of closure curves, then we can have the integral as sum of that integrals. Suppose if we have 4 closure curves inside C, then the integral along the C is equal to sum of the integrals along the 4 closure curves. This is the extension of the Cauchy theorem for multiply connector regions. Next, the second theorem is Cauchy's integral formula. It is the Cauchy's integral formula. According to this theorem, the function f of z should be in the form of some function by single factor with the power 1 or some function by single factor power n, like this. Both are of same form only. The function should be in the form of like this, something by single factor power something. And two conditions for this. Whatever you write the function in the numerator, this function should be analytic inside C on C only. The numerator function phi of z should be analytic inside C on C only. And from the denominator, this point z0 should lie inside the region only. The point should lie inside the region only. These two conditions satisfy, we can find the integral of this complex function by using this Cauchy's integral formula only. Right? If you want to do the integral of complex function f of z along the closure curve, the two conditions are like this. The function should be in the form of like this, and the numerator function should be analytic inside C on C, and the point z0 should be inside the region. These two conditions satisfy, we can find the integral of complex function along the closure curve using this theorem only. So we have two theorems. One is Cauchy's theorem, other one is Cauchy's integral formula. Using these two theorems, we try to evaluate the integral of complex function along the given closed curves. That closed curve may be in the form of any form, but we do the problem for closed curves using the theorems only. Now this is a statement. If a function f of z is of the form phi of z by z minus z0 or phi of z by z minus z0 power n, where the numerator function phi of z is analytic at every point inside C on C, that too here it is a simple closure curve, and z0 is any point inside C, then integral of this function is equal to 2 pi I into this function value at a point z0. Suppose if we have power n, 2 pi I by n minus 1 factorial into n minus 1th derivative of this function, n minus 1th order derivative of this function at a point z0. This is the value of this integral. It is the value of this integral. So these two theorems, Cauchy's theorem and Cauchy's integral formula, are applicable for evaluation of the integral along the closure curves. Now next we'll discuss about the method of evaluation of integral using the theorems, or we discuss about the procedure for the evaluation of complex integral along the closure curve. Procedure for the evaluation of complex line integral along the closure curve. If you are given some integral with a function along some closed curve or some closed region, or the integral is given along with a closed curve or closed region, we follow this step by step procedure for the evaluation of integral. Step number 1. Whatever the function is given inside the integral, let us choose that function as f of z. That is the first step on. Let f of z equal to whatever the function is given here, take this as function f of z. It is the first step. Next, step number 2, find the singular points. Find the singular points. In short form, s dot pt of f of z. It is the second step. Already we have seen the how to find the singular points only. First of all, singular point means if a function is not defined, not differentiable, or not analytic at any point, then such a point is called singular point only. So finding the singular points is the second step. Next, third step, drawing the region. Drawing the region with a given equation of curve. Draw the region or with given equation of curve. Equation of curve C. Draw the region or with a given equation of curve C. Next, step number 4. After drawing the region with the given equation of the curve, region R or closed curve C, we check whether the singular points lie inside the region, on the region, or outside region only. After drawing the region, we can check the singular points of the function lie inside the region or outside region like this. Suppose inside the region there is no singular point. Inside the region, on the region, there is no singular point. In this case, we apply the first theorem, Cauchy's theorem only. We apply the Cauchy's theorem. According to Cauchy's theorem, the integral over C f of z dz equal to 0. The singular points of the function. The function may have singular points. The function has singular points. This may have one or more than one singular point. Even though the singular points exist for the function, they do not lie inside C on C, then we can write the integral of that function is equal to 0 only. So inside the region, no singular point. On the region, no singular point means the singular point of the function lie outside the region only. Right? If a function has one or more singular points, we check the singular points lie inside the region, on the region, or outside the region only. Suppose inside the region there is no singular point, on the region there is no singular point, means the singular point lie outside the region only. In such case, integral of the function along the closure curve is always 0 by first theorem, Cauchy's theorem only. Suppose the singular points lie inside the region at one or more points. At one or more points. The singular points of the function lie inside the region. One of the singular point lies in the region or more than one singular point lie inside the region. In such case, we apply the second theorem, Cauchy's integral formula. Right? Now, this is the procedure for the evaluation of integral of complex function along the closed curve or over the closed regions. So whatever the function is given inside the integral, we take that function as f of z. Next, we find the singular points of the function and draw the region. After that, we check the singular points lie inside the region, on the region, or outside region. Based on that, we apply the particular theorem only. That is, it is the method of choosing the particular theorem depending on the problem for the evaluation of the integral. It is a procedure only. Now let us do the problems on this, the complex integral. Now, it is a first problem. the value of the integral z plus e power z by z minus 4 into z plus 2 power 3 dz, where c is mod z minus 2 equal to 1. We are asked to find the integral of this function along this curve c, that c is given by this. Now it is the equation of the circle. It is the equation of the circle. Already we know that equation of the circle with the center at origin and radius r is x square plus y square equal to r square. It is the equation of the circle with center at origin and radius r. The same equation of the circle can be written in terms of z notation like this: mod z equal to r. Both are equation of circle with center at origin and radius r only. It is in terms of x and y, it is in terms of z only. It is a particular center at origin only. And if you consider the general center at any point, x minus x naught whole square plus y minus y naught whole square equal to r square. This equation of the circle in terms of z is written as mod z minus z naught equal to r only. It is the equation of circle, it is also equation of circle, it is in terms of x and y, it is in terms of z, it is in terms of x and y, it is in terms of z only. Here general center, any general center x naught, y naught, radius r. Here particular center origin and radius r only. Right? Now if you consider the inequality like this, mod z minus z naught less than r. This inequality says that the point z lies inside the circle with center at z naught radius r only. Suppose if you consider a circle with center at z naught radius r, this inequality says that the point z lies inside the region only. If we write the inequality mod z minus z naught greater than r, this greater than inequality says that the point z lies outside the region only, or outside the circle only. And this says that the point lies on the circle only. It is on the circle, it is interior to the circle, it is exterior to the circle. Just we require this equation of circle with a particular center origin, it is at any center x naught, y naught only. Now just we go back to this problem. So we are given this problem along with equation of circle mod z minus z naught equal to r. Z naught is here 2 and r is 1. Center is at 2, radius is 1. It is a closed curve. We are given integral of the function along with a closed curve. Because of closed curve, we follow this step-by-step procedure only. If you are given integral along with a closed curve, then we follow the step-by-step procedure only. According to this step, whatever the function is given inside the integral, we choose that function as f of z only. Now let us do this problem. In the solution, let us consider the function f of z. Whatever the given inside the integral, we choose that function as f of z. Z plus e power z divided by z minus 4 into z plus 2 power 3 on. It is a given function. With this, first step is completed only. Next, according to second step, we should find the singular points of the function. It is in the form of something by something, numerator by denominator. Now in the numerator, we have a sum of the two functions. Only z is polynomial function, it is a standard function. We know that it is everywhere analytic. Next, exponential function is also standard function. It is also analytic at every point. When two functions are analytic, sum of the two is also analytic at every point. Only numerator function is analytic at every point only. Now let us consider the denominator part. It is a polynomial because z minus 4 power 1. The power of this factor is positive integer. It is a polynomial function, first order polynomial. Z plus 2 power 3. It is a cubic polynomial. It is a first order polynomial, linear polynomial, cubic polynomial. Product of these two is also polynomial. That product will be fourth order. We know that every polynomial is analytic at every point. numerator function is analytic at every point, denominator function is also analytic at every point. But if you consider total function, this total function will be analytic at every point when the denominator is not equal to 0 only. But the denominator is 0 only for z equal to 4 and minus 2 only. So this function is not defined at 4 and minus 2 only. That is why 4 and minus 2 are singular points of this function. Or if you want to find the singular points of this function, simply equate denominator function to 0 and solve for z. The singular points of this function are given by this. The singular points of this function are given by this equation only. Equate denominator to 0, solve for z only. If you solve for z, this will give z equal to 4 and minus 2. These two are singular points of this function. Or directly we can say this function is not defined at 4 and minus 2. Therefore, 4 minus 2 are singular points of this function. Here the singular points are z equal to 4 and z equal to minus 2 only. These two are singular points. So up to here, second step is completed. Next, third step. What is the third step? Drawing the region with a given equation of the curve only. Actually, we are given equation of circle. Because of the circle, no need to draw the diagram. Without drawing the diagram also, we can say the point is inside the region or outside region or on the region only. With 3 these. With equal, with less than, greater than, we can set the point is inside the region, on the region or outside region only. This satisfies, we can set on the circle. This satisfies, we can say point is inside the region. This satisfies, we say that point is outside region only. So whenever circular region is given, no need to draw the diagram. Even if we draw also, we can check only. Let us draw the diagram. The center is 2, radius is 1 only. Zero, 1, 2, 3, 4, 5, and so on. 1, minus 1, minus 1, 2, minus 2. Now center is 2, radius is 1. Now this is the our given closed curve C, or this is a region R. So we are given this region only, or we are given the closed curve C only. Now we'll check the singular points lie inside the region, on the region, or outside region only. First step is choosing the function as f of z. Second step is finding the singular points. Third step is drawing the region. Okay. But from the next problem onwards, if it is a circular region, no need to draw the diagram. Without drawing the diagram also, we can check inside, outside, or on. I will show you later on. Or if you draw the diagram also, directly we can set inside the region, outside region, on the region only. Now let us take the first singular point, 4. Z equal to 4. We can write the z equal to 4 as 4 plus I0. 4 plus I0, just like x plus IY. Or we can write this as 4 comma 0. 4 comma 0. Y coordinate 0, so this point lies on x-axis. But here x coordinate is positive, so this lies on positive x-axis only. On positive x-axis, we can find this point 4 comma 0 only. This is the point. So the first singular point is lying outside the region or outside the closed curve only. So we do not require this outside region. Next, the second singular point is z equal to minus 2. Z equal to minus 2. We can write the minus 2 as minus 2 plus I0, or minus 2 comma 0. Again, y coordinate is 0, so this point lies on x-axis, and x coordinate is negative, so this point lies on negative x-axis only. That is this point. It is a minus 2 only. The function has only two singular points. The two singular points are lying outside the region or outside the closed curve only, not inside the region, not on the region. So the singular points are not inside the region, not on the region, means this function is analytic inside the region, on the region only. So whenever function is analytic inside the region, on the region, then we evaluate this integral by using the Cauchy's integral theorem or Cauchy's theorem only. Okay. So up to here, we know that the singular points are lying outside the region. That is why we say function is analytic inside C on C only. And we can write the integral value directly by using the Cauchy's theorem only. But before writing that theorem, here I will show you how to check the point lies inside region, on the region, outside region without drawing the diagram only. Now we take the LHS part of this circle. We take the LHS part of this circle, modulus of z minus 2. And if you want to check this point is inside the region, on the region, outside region, take this point 4, substitute here, that is modulus of minus 4 minus 2 equal to modulus of 2. Modulus of 2 is plus 2. This is LHS part, and we compare this LHS with the RHS of this equation. Here LHS is 2, it is greater than RHS of the equation 1. From this we can say that the greater than inequality is satisfied only. The greater than inequality is satisfied. Whenever the greater than inequality satisfies, we can say that the point lies outside region only. So simply take the 4, substitute here, 4 minus 2, 2, modulus of 2 is plus 2 is greater than 1. Therefore, the point lies outside region only. Similarly, we can check the another point. Take the minus 2, substitute here, minus 2, minus 2, minus 4. Modulus of minus 4 is plus 4 is greater than 1. So this point also lies outside region only. Like this, we can say directly lies inside the region or outside region or on the region only without drawing the diagram. Whenever circular region is given, don't draw the diagram. Without drawing the diagram, directly we can set here itself inside the region, on the region or outside region only. So now let us come to this problem. Here the function has two singular points. The two singular points are lying outside region. That is inside the region no singular point, on the region no singular point. That means function is analytic inside C on C only. Therefore, by Cauchy's theorem, integral of this function along the closure curve is always 0. Therefore, by Cauchy's theorem, we have integral over C f of z dz equal to 0. So like this, we can do the problem with a step-by-step procedure. So answer is A. Let us go to the next problem. Now this is a GATE question. This question was given in the year 2021. Let us read the question first. Let f of z equal to 1 by z square plus 6z plus 9 defined in the complex plane, full stop. The integral f of z dz over the contour of a circle with a center at origin and unit radius is. Again we are given the curve, and it is the curve is here closed because we are given circle with center at origin and radius. We are not given any condition on the circle only. That is above the x-axis, below the x-axis, or left of the y-axis, right of the y-axis, in first quadrant, second quadrant, third quadrant, fourth quadrant, like this, no condition. We are not given any condition on this circle, means we are given that it is a, we are given that closure curve only. So we are given integral of the function along with the closure curve only, and the closure curve is circular curve only with the center at origin, radius 1. So let us do this problem by our step-by-step procedure because it is a closure curve. That is why we follow our step-by-step procedure on. Now let us start the problem. According to our step-by-step procedure, whatever the function is given inside the integral, we take that function as f of z. Already it is given that f of z. According to our procedure, we take this as function f of z. F of z equal to 1 by z square plus 6z plus 9. Next, second step is finding the singular points. Next we find the singular points. Now to find the singular points, just look at this, something by something only. this is defined for all the values of z except this is equal to 0 only. Whenever this is 0, this becomes infinite only. That is why to find the singular points, equate denominator to 0, solve for z only. It is also same as the z plus 3 whole square. It is a perfect square. It is a quadratic expression. This is in the form of perfect square, a plus b whole square form only, a square plus b square plus 2ab form. So finally, this is not defined at z equal to minus 3 only. Z equal to minus 3 is a singular point. The function has only one singular point. The function has only one singular point, z equal to minus 3 only. And the region will be bounded by the equation of the circle, the unit circle. Center, mod z minus z naught equal to r. R is 1, center is 0 only. So mod z equal to 1. It is the equation of the circle with center at origin, radius r on. The region will be bounded by the closure curve C like this. Next, we check the singular point lies inside the region, on the region, or outside region. So whenever circular region is given, no need to draw the diagram. Directly, we can check the point is inside the region, on the region, or outside region only. An easy way to check the inside, outside, or on, we take this point, we substitute here, we check whether this is greater than radius or less than radius or equal to radius only. If you substitute minus 3 here, modulus of minus 3 is plus 3. Plus 3 is greater than radius. So this point is lying outside the region only. Wherever the point lies outside region, we do this problem by Cauchy's theorem only. Therefore, by Cauchy's theorem, integral over C f of z dz equal to 0. According to Koch's theorem, directly we can have the integral value like this only. Because the function has only one singular point and it is lying outside the region, not inside the region, not on the region. That is why by Koch's theorem, the integral of this function along the closure curve is always 0. It is a numerical answer question and the answer is here 0. Okay, let us go to the next problem. It is also a 2021 gate question. Let us read the question. Let C represent the unit circle centered at origin in the complex plane. C represent the unit circle centered at origin in the complex plane. And complex variable z equal to x plus iy. The value of the contour integral, where integration is taken counterclockwise. Counterclockwise means anti-clockwise. Anti-clockwise is the positive direction only. Unless otherwise stated, we always take the anti-clockwise direction only. So we are given unit circle. We are given unit circle centered at origin. Again, we are given the modulus of z equal to 1. And there is no condition on the circle. That means we are given again closure curve on. So we are asked to find the integral of this function along the closure curve or over the closure region only. That is why again we follow our step-by-step procedure according to our procedure only. So let us do this problem by our step-by-step procedure according to our method or procedure. Whatever the function is given inside the integral, we take this as function f of z only. Let f of z equal to cos h 3z by 2z. Let f of z equal to cos h 3z by 2z only. Next, singular point. This function is in the form of something by something. Only numerator is cos hyperbolic. But cos hyperbolic is the one of the standard function. It is analytic at every point. In the denominator, 2z is a polynomial, first order polynomial. It is also analytic at every point. Analytic at every point, analytic at every point, but both together, the ratio, this is not defined at z equal to 0 only. Only cos is analytic, only z is analytic, but cos and z together, this total function is not defined at z equal to 0 only. So z equal to 0 is one of the singular point of this function. Then singular point is z equal to 0 only. And the region will be bounded by the curve C mod Z equal to 1. That is, we are given unit circle only. So, unit circular region only. These steps are computed. Next, fourth step. According to first step, we check this point lies inside the region, on the region, or outside region. Based on that, we can find the integral value by using the two theorems. Z equal to 0. Modulus of 0 is 0. 0 less than 1. So the point is lying inside the region only. Wherever the point lies inside the region, we try to do this problem by Cauchy's integral formula. But to apply Cauchy's integral formula, the function should be in the form of like this. The given function should be in the form of something by single factor or something by single factor power something like this. If you want to do this problem by Cauchy's integral formula, the function should be written in the form of like this. Some function by single factor or some function by single factor power something like this. After expressing this function like this, we verify the two conditions. For numerator, we have one condition. For denominator also, we have one condition. According to theorem, the condition is like this. Whatever you take the function in the numerator, this function should be analytic inside C on C. Outside the region, that may or may not be analytic, doesn't matter only. But inside the region, on the region, it should be analytic only. Next, from the denominator, this point Z should lie inside the region. That is the condition. Right? This point should be inside the region, and this should be analytic at every point inside C and on C only. So these are the conditions only. If these two conditions satisfy, we can do the problem by Cauchy's integral formula only. Check whether it is in the form of any one of these or not. Directly it is not in the form of this, but we can express this in the form of this. Because in the denominator for this we have a power 1 only. So we can write this function in the form of like this, something by single factor only. This is equal to cos h 3z by 2 whole divided by z minus z naught form only, that is 0. So this function is in the form of some function by single factor only. It is just like phi of z by z minus z naught form only. Now here phi of z is cos h 3z by 2 and z naught is 0 only. Now after writing like this, we check the conditions of the theorem. According to theorem, this point z naught should lie inside the region and this function should be analytic inside the region, on the region only. But this point is already inside the region only. First condition satisfied. Next, second condition, it should be analytic inside C, on C or not, check it on. According to theorem, it should be analytic only. Now we check whether it is analytic or not. First of all, the cos hyperbolic is standard function. Why it is standard function? It is defined continuous differentiable analytic at every point in the whole complex plane only. Whenever it is analytic at every point in the whole complex plane, in the particular region also, the function will be analytic only. So this function is analytic inside C, on C, and the point is inside the region. Therefore, we can do this problem by Cauchy's integral formula because the two conditions of the theorem are satisfied. So we can apply the theorem for this and we write the value of the integral by theorem only. Therefore, by Cauchy's integral formula, we have integral over C f of z dz equal to 2 pi I into phi of z naught. Here z naught is 0 only. In this function, substitute z equal to 0 only. Equal to cos h 3 0. 3 into 0, 0, cos h0 is 1 because cos hyperbolic is e power x plus e power minus x by 2 only. When you substitute when you substitute 3z in place of x, then that will be cos 3z, cos h3z equal to e power 3z plus e power minus 3z by 2 only. When you substitute z equal to 0, that becomes 1 plus 1 by 2, 1 plus 1 by 2, 2 by 2 is 1. So its value is 1 into 2 pi. So answer is 2 pi. Cos h0, cos h0 is 1 by 2 into 2 pi. This is equal to pi I. Cos h0 is 1 by 2 into 2 pi. So finally the answer is pi I. This is given in the option D. It is also a GATE question. This question was given in the year 2021. So first we have to check the curve is closed or not, the region is closed region or not. If it is closed curve, then we follow our step-by-step procedure and we do the problem by our one of the theorem only. Because for closed curves we have two theorems, one is Cauchy's theorem, other one is Cauchy's integral formula. Depending on the function and the points, we can choose one of the theorem and we write the value of the integral like this. Now, let us go to the next problem. Now it is also a GATE question. This question was given in the year 2021. It is a multiple choice question. Let us read the question. Let minus 1 minus j instead of I, j is given. It is only difference only. We can treat the here j equal to I only. Minus 1 minus j, 3 plus j and minus 1 plus j be the vertices of a rectangle. Already name of the region is given. What is the name of the region? Rectangle only. For the rectangle, we can find the four vertices. All the four vertices are given in the complex plane. This rectangle is given in the complex plane. Assuming that C is traversed in counterclockwise. Assuming that C is traversed in counterclockwise. Counterclockwise means like this direction. Anti-clockwise is the positive direction. That positive direction is the counterclockwise direction. The value of the contour integral, the value of this contour integral, that is integral along the curve C, is the contour integral. Now we require the value of this integral only. So integral is given along with the closed curve or closed region. Because of the closed region, closed curve, we try to do this problem again by our one of the theorem only, according to our step-by-step procedure. So let us do this problem by step-by-step procedure only. Now, according to our procedure, whatever the function is given inside the integral, choose this function as f of z only. Let f of z equal to 1 by z square into z minus 4. It is the first step only. According to the second step, find the singular points. Then the singular points are z equal to 0 and z equal to 4. Why these two are singular points means this function is in the form of something by something. The function is in the form of something by something. Only one is constant polynomial at every point it is analytic. In the denominator it is also third order polynomial, it is also analytic at every point. But if we consider the total ratio, this is not defined at z equal to 0 and z equal to 4. That is why these two are singular points of this function. This function is analytic at every point except the 2 points on, because it is not defined at these 2 points. So these two are singular points of this function. The function has 2 singular points on. Up to a second step is completed only. Next, third step. According to third step, we need to draw the diagram. If it is circular region, no need to draw the diagram. But it is not a circular region, it is rectangle. Because rectangle, we draw the diagram only. Here, R is the rectangular region with vertices. we should draw the rectangular region with the vertices. The vertices are here minus 1 minus j. That is, it is in the form of x plus iy. Every x plus iy can be written in other form as a coordinate of a point or ordered pair of two real numbers like this, x comma y only. So x plus iy will be written in the form of x comma y. That is why here we can write this as minus 1 comma minus 1. The first vertex is minus 1 comma minus 1. Next, second vertex is 3 minus j, means 3 comma minus 1. Next, third vertex is 3 comma 1, and fourth vertex is minus 1 comma 1. Now we are given rectangular region with the 4 vertices only. If you observe the first one, both x and y are negative, means this lies in third quadrant only. Now in this, x is positive but y is negative, this lies in fourth quadrant only. Both are positive, x and y are positive, so this lies in first quadrant. And x is negative, y is positive, so it lies in second quadrant only. So let us draw this diagram, and then we check the singular points lie inside the region, outside region, on the region or not. X-axis, y-axis, zero, 1, 2, 3, 4, minus 1, minus 2, minus 3, 1, 2, 3, minus 1, minus 2, minus 3, and so on it is. The first point is, the first point or first vertex is minus 1 comma minus 1. It lies in third quadrant. Minus 1, minus 1. This is the point. Next, second vertex is 3 comma minus 1. 3 comma minus 1. Next, third vertex is 3 comma 1. 3, 1. X is 3, y is 1. So this is a 3 comma 1 vertex. The last vertex is minus 1 comma 1. Minus 1 comma 1. Right. Now we draw the diagram. The direction of this closure curve is in anti-clockwise direction like this. Anti-clockwise direction. We are already given that anti-clockwise direction. Now it is a rectangular region only. What are the singular points here? 0, 4. We check 0 lies inside the region or not, 4 lies inside the region or not. 0 is inside the region, but 4 is outside the region only. The function has two singular points, 0 and 4. Out of two singular points, only one of the singular point is lying inside the region. One is lying outside region only. All singular points may lie inside region, all singular points may lie outside region, or some of them lie inside the region, some of them lie outside region also. Out of two singular points, one is inside the region, one is outside region. One or more lie inside the region, then we apply the Cauchy's integral formula. There is no singular point inside the region, then we apply directly Cauchy's theorem only. But here one of the singular point is inside the region only. So we do the problem by Cauchy's integral formula. We do this problem by Cauchy's integral formula. But according to formula, the function should be like this only. The function f of z should be in the form of phi of z by z minus z naught, or phi of z by z minus z naught only. We should express this function in the form of like this, if it is not in the form of like this only. After writing like this, we verify the conditions only. According to the conditions of the theorem, the numerator function should be analytic inside C on C, and this point z0 should lie inside the region only. These are the conditions only. Now this is a singular point inside the region. It is lying outside the region. We never consider this. Just focus on the singular point inside the region only. Only one is inside the region. Only one singular point is inside the region only. And this 0 is coming from this factor, not coming from this factor only. So this 0 singular point is coming from this factor. So keep this factor in the denominator and take the remaining function as a numerator function for writing this form only. This is equal to 1 by z minus 4 as a numerator function. In the denominator, we write the z minus z naught power n form only. That's all. Right? So we are writing the function f of z in the form of like this, something by single factor only. Now we can verify the conditions of the theorem for this. This is analytic at every point except 4. That 4 is not inside the region, 4 is outside the region only. That is why this is analytic inside the region, on the region only. And this point is 0, that 0 is inside the region only. The two conditions of the theorem are satisfied. So we can evaluate the integral by using Cauchy's integral formula. Now, by Cauchy's integral formula, we have integral over C f of z dz equal to integral over C, phi of z is 1 by z minus 4, in the denominator z minus 0 power 2 dz. This is equal to 2 pi I by, it is power n. If it is n, in the denominator n minus 1 factorial and n minus 1 times derivatives on. So 2 pi I by 2 minus 1 factorial into phi dash because 5 power n minus 1 times derivative, that is 2 minus 1 times derivative at a point z0. Z0 is here 0 only. That is 2 pi I by 1 factorial is 1 and 2 minus 1 times derivative, that is 1 time derivative only. It is same as the phi dash function at a point z equal to 0 only. This is same as the phi dash of 0. Phi dash of 0 means phi dash of z at z equal to 0 only. But this is a function phi of z only. The derivative of this function is minus 1 by z minus 4 whole square. Right? At z equal to 0. Z equal to 0 minus 4 whole square 1 by 16 and 2 8 times 1. So it is minus pi I by 8. Or in the problem itself, instead of I, j was given only. So instead of I, we can take the j, that is minus pi j by 8 or minus pi I by 8. Now this is the value of this integral for a given closure curve along this rectangle only. That is minus pi j by 8. It is the correct answer. So like this we can do the problem by Cauchy's integral formula because of the singular point is inside the region only. It is also the previous GATE question. This question was given in the year 2021. It is a multiple choice question. So let us go to the next problem. given z equal to x plus iy, I equal to root of minus 1, C is a circle of radius 2. C is a circle of radius 2 with the center at the origin. Center at the origin. General equation of circle with center at z0 radius r is like this. The general equation of the circle with center at z0 radius r is this. And here this radius is 2. This is 2 and z0 center. Center at the origin means this is 0. So finally this becomes mod z equal to r. It is the equation of circle. R is here 200. This is the given equation of circle with center at origin radius 200. The contour C travels in anti-clockwise, then the value of the integral round off to 1 decimal place. It is also GATE question. This question was given in the recent year 2022 and it also fill in the blank question. Numerical value answer. Round off to 1 decimal place on it. Integral is given along with the closure curve. So again we try to do this problem by our step-by-step procedure only. According to our method, whatever we have given function inside the integral, we take this function as the function f of z only. Let f of z equal to 1 by 2 pi into z minus I into z plus 4i. It is a function. Something by something. For the existence of this ratio, denominator part must be not equal to 0. But here denominator is 0 only for I and minus 4i. So the singular points of this function are I and minus 4i. Z equal to I and Z equal to minus 4i. These two are singular points. Up to here, second step is completed. Next, we go to third step. According to third step, we need to draw the diagram, but no need to draw the diagram because it is a circle only. Here, R is a circular region bounded by the equation of circle mod Z equal to 2 only. Now, we'll check whether one by one, whether this lies inside the region, on the region, or outside region. Whether it lies inside the region, on the region, or outside region only. When you substitute Z equal to I here, that is modulus of x plus iy equal to under root of x square plus y square. The modulus of x plus iy is same as under root of x square plus y square. So modulus of I means modulus of 0 plus I, that is equal to 1, right? This is here, and modulus of this is 1, 1 less than 2. So less than inequality satisfied means this point lies inside the region only. Next, we go to second singular point, minus 4i. Minus 4i. Zero plus minus 4 into I. Modulus of x plus iy, which is equal to under root of x square plus y square, that is 16 under root. This is equal to 4. But 4 is greater than 2 only. So this point is lying outside region and this point is lying inside region only. The function has two singular points, but out of two, only one of the singular point is inside the region. One of them is lying outside region only. Similar to previous problem only. The function has two singular points, out of two, only one is inside region. One or more singular points lie inside the region, then we apply the Cauchy's integral formula. According to Cauchy's integral formula, this function should be in the form of like this. Some function phi of z by single factor power 1 or power something, right? Now here for both factors powers are 1, so we should write this in the form of like this, something by single factor only. So this is equal to, now to write this in this form, the denominator point should lie inside the region, and this should be analytic inside the region, on the region only. So whatever take the point, whatever take the factor in the denominator, that factor will give the point z0, that z0 should lie inside the region only. Like that here also, this singular point is lying inside the region and this point is coming from this factor. So keep this factor in the denominator and take the remaining function as numerator function only. To express this given function in this form, so take this factor z minus I in the denominator, because we are getting a singular point from this factor only. And take the remaining function as numerator function, 1 by 2 pi into z plus 4I. This is the phi of z function by z minus z0 form only. Now by Cauchy's integral formula, we can write this value only. Therefore, integral over C f of z dz equal to 2 pi I into phi of, it is a phi function of z0. What is the z0 here? I. Substitute I in place of z in the function phi of z only. This is equal to 2 pi I. Here phi of z function is 1 by 2 pi into z plus 4I at z equal to I. 2 pi get cancelled. After substituting z equal to I, this becomes phi I get cancelled. This is equal to 1 by phi. Now it is a fill in the blank question, and we should round off this to one decimal place. So this is equal to 0.21. Right? This is our value of the integral only. This is the value of our given integral along the given closure curve only. So like this we can do the problem by the Cauchy's integral formula or Cauchy's theorem for closure curve, depending on the singular point. The singular point lies inside the region, then we apply the integral formula. No singular point inside the region, on the region, then we apply the Cauchy's theorem only. But here one of the point is inside the region, that is why we have done this by Cauchy's integral formula only. This is the recent GATE question. The question was given in the year 2022, that to fill in the blank question. Let us move to the next problem. Now before going to this next problem, I'll write the another problem here. The value of integral over C 1 by z minus 1 into z minus 2 dz, where C is mod z equal to 3 comma is. Now this is the problem. Again we are given the integral along with the equation of circle, right? And we are not given any condition on the circle. That is why it is a closure curve. Because of closure curve, we follow our step-by-step procedure only. According to our step-by-step procedure, we take the function as f of z, let f of z equal to 1 by z minus 1 into z minus 2 only. Then the singular points. The function has two singular points, 1 and 2 only. This function is not defined at 1 and 2 only. So the function has two singular points only. Up to here, second step is coming. Next, third step. According to third step, we have to draw the diagram. But no need to draw the diagram because of this circular region. Without drawing the diagram also, we can say the point is inside the region, on the region, or outside region only. Or is the region bounded by the circle mod z equal to 3 only. Next, check one by one. Inside the region, on the region, or outside region only. 1 less than 3 inside the region. 2 less than 3 inside the region. The function has two singular points. The two singular points are lying inside the region only. Whenever more than one singular point lie inside the region, we try to do this problem by partial fraction method or without partial fraction also. There are two methods only. Here I will show you the two methods for the evaluation of this integral. The two singular points of the function are lying inside the region only. Whenever one or more lie inside the region, whenever one singular point lies inside the region or more than one singular point lie inside the region, we try to do the problem by Cauchy's integral formula. According to formula, we should write this in the form of something by single factor only. Suppose if I write like this, 1 by z minus 2 divided by z minus 1, it's a phi of z by z minus z naught form only. This is inside the region and this is having singular point at 2. 2 is inside the region, so this function has singular point inside the region only. The condition of the theorem is failed. That is why directly we cannot apply the theorem for this only. So whenever more than one singular point lie inside the region, we try to do this problem by partial fraction method or without partial fraction also. First, we try to do this problem by partial fractions method only. Method 1 by partial fractions only. First, where the partial fractions of this. F of z equal to 1 by z minus 1 into z minus 2. Its partial fractions are 1 by z minus 2 minus 1 by z minus 1 only. After splitting into partial fractions, we'll have a simple functions like this only. Now we take the integration on both sides. Integral of f of z dz equal to integral over c 1 by z minus 2 dz minus integral over c 1 by z minus 1 dz equal to. Now we are asked to find the integral of this function along this closure curve C only. And this point is inside the region only. The numerator is phi of z function. This is z naught only. But the numerator function is constant. Constant polynomial is everywhere analytic only. This is analytic inside the region, on the region, and the point is inside the region. So we do this problem by Cauchy's integral formula by first result only. Again here, one is constant polynomial. It is analytic at every point inside the region, on the region, outside the region only. And this point 1 is inside the region only. So for each integral, we can apply the Cauchy's integral formula and then we write the value of the integral only. Now for first one, 2 pi I into, substitute this 2 in the numerator function, but here constant, it is constant. So 1 plus, sorry, it is minus, between these two we have minus, so minus 2 pi I into phi of z function at z equal to 1 only. Again here phi of z is 1, constant only, it is also 1. Right? So 2 pi I minus 2 pi I, this is equal to 0. This is the value of the integral using partial fraction method only. Why we are using the partial fractions means directly we cannot express this in the form of function phi of z by z minus z naught only. We can write, but the condition of the theorem is failed only. That is why we are going for partial fractions like this only. This is the first method only. Next, second method, without partial fractions only. with a 2. Mod z equal to 3. Zero, 1, 2, 3, minus 1, minus 2, minus 3, 1, 2, 3, minus 1, minus 2, minus 3 only. Our singular points are 1 and 2 only. 1 is one singular point and 2 is another singular point. The function has two singular points, 1 and 2, both are lying inside the region only. Both are lying inside the region. Counterclockwise or anti-clockwise or positive direction only. The curve is closed, always the orientation must be in anti-clockwise only. That is the positive direction. Right? So we have two singular points inside the region. Let us consider some circle with the center at 1. Let us consider circle with center at 1. Say this C1. Let us consider another circle with center at 2. But these two circles should not overlap only. We can consider any small radius also. We can consider small radius only. Draw the circle with center at 1, draw the circle with center at 2, and these two should not intersect only, like that. Take a small radius also. Okay? This region should not contain the other singular point of the same function. Let us suppose this is C2. Let us suppose this is C. Now see this. The function is analytic inside C, outside C1, outside C2 only. Not within C1, not within C2 only. So by Cauchy's theorem for multiply connected region, we can write this integral. We can write the integral as like this. Integral over C f of z dz is equal to integral over C1 f of z dz plus integral over C2 f of z dz only. So by Cauchy's theorem for multiply connected region, we are writing the integral along the closure curve C as integral along C1 plus along C2 only. Integral along this curve is same as along this plus along this only. This is equal to integral over C1. C1 is a circle with center at 1 with some small radius only. And the function is 1 by z minus 1 into z minus 2 dz plus integral over C2 1 by z minus 1 into z minus 2 dz only. So evaluate this integral along the circle C1 only. Along this integral, evaluate the integral along the circle C2 only. This is along the C2, it is along the C1 only. Integral along the C is same as the integral along C1 plus along C2 only. Now, let us evaluate this by using the Cauchy's integral formula. The function is having two singular points, 1 and 2, but only 1 is inside the C1 and 2 is outside C1 only. That is why we write this as like this. 1 by z minus 1. In the numerator, we write the 1 by z minus 2 like this. We are evaluating this along the circle C1 only. Within the C1, it is analytic at every point, and this point is inside region. By Cauchy's integral formula, we can evaluate this only. Plus, we should evaluate this second integral along the circle C2 only. The C2 is containing the singular point at 2. 2 is coming from this factor. So keep the factor in the denominator and take the remaining function as numerator function 1 by z minus 1 dz only. And for each integral, apply the Cauchy's integral formula. Phi of z by z minus z naught. Phi of z by z minus z naught only. This is equal to 2 pi I into, in this function, substitute z equal to 1 plus 2 pi I into 1 by z minus 1 at z equal to 2 only. When I substitute this z equal to 1, this becomes minus 2 pi I plus, when I substitute z equal to 2, 2 minus 1 is 2 pi I. So answer is 0 only. This is the value of the integral. So here we have done the problem by Cauchy's integral formula only without any partial fraction only. So like this we can do the problem in two methods, by partial fractions, without partial fractions only. Now this is the simple method only, and for this method no need to draw the diagram. Diagram is not required. Depending on the number of singular points inside the region, we can write the integral as sum of the integrals only. Suppose there are 3 singular points inside the region, then write the integral as sum of 3 integrals and directly evaluate it. We do not require this diagram only. So let us do another problem of the same model. This one. The value of this integral where c is mod z equal to 4 only. The function has 3 singular points, 1, 2, 3. All 3 singular points are inside the region only. So whenever more than one singular point lie inside the region, we try to do this problem by two methods. One method is verification, one method is the partial fraction method, other method is without partial fractions only. So here we do this problem by without partial fractions only. That is a simple method only. Here how many singular points are there? 3 singular points. Because of 3 singular points, we write the integral as sum of 3 integrals only. Integral over c f of z dz equal to integral over c1 z by z minus 1 into z minus 2 into z minus 3 dz plus integral over c2 z by z minus 1 into z minus 2 into z minus 3 dz plus integral over c3 z by z minus 1 z minus 1 into z minus 2 into z minus 3 dz. Right? Now this is along the C1, along C2, C3. Let us suppose the C1 is a circle with center at 1, C2 is a circle with center at 2, C3 is a circle with center 3 only. So this C1 contains only one singular point, C, 1 only. C2 contains singular point only 2, C3 contains singular point 3 only. So diagram is not required. Because of 3 singular points inside the region, we are writing the integral sum of 3 integrals only. Let us suppose C1 is a circle with center at 1 only. So keep this factor in the numerator and take the remaining as numerator function only. Integral over C1 like this. Z by Z minus 2 into Z minus 3 dz like this. Phi of Z by Z minus Z naught. Let us suppose C1 is a circle with center at 1. And this is not containing the 2 and 3 only. So that is why it is analytic at every point inside C on C1 and the point 1 is inside the region only. Integral over C2 Z by Z minus 1 into Z minus 3 in the denominator Z minus 2 dz plus integral over C3 in the denominator Z minus 3 Z by Z minus 1 Z minus 2 dz on. Phi of Z by Z minus Z naught, phi of Z by Z minus Z naught, phi of Z by Z minus Z naught only. This is for C3. So for the first integral, we apply the Cauchy's integral formula 2 pi I into phi of Z naught. Z naught is 1. In this numerator function, substitute Z equal to 1 only. z by z minus 2 into z minus 3 plus 2 pi I into z by z minus 1 into z minus 3 at z equal to 2 plus 2 pi I into z by z minus 1 into z minus 2 at z equal to 3 only. 2 pi into phi of z naught, 2 pi into phi of z naught, 2 pi into phi of z naught only. For this integral phi of z is this, for this integral phi of z is this, phi this, it is a phi of z only. Now 2 pi I is common from each and every term. Substitute z equal to 1, 1 by minus 1 into minus 2 plus z equal to 2, 2 by 2 minus 1, 1, 2 minus 3 minus 1 plus z equal to 3, 3 by 3 minus 1, 2, 3 minus 2, 1, 3 by 2 only. 1 by 2, 3 by 2, 4 by 2, that is 2, 2 minus 2, sum is 0. It is the value of the integral. So like this, more than one singular point lie inside the region, we try to do the problem by like this simple method only, without any partial fraction. We can do the problem like this only. Depending on the number of singular points, we write the sum of the integrals, and then we apply the Cauchy's integral formula directly like this. This is simple method. So answer is 0. So this is about the method of evaluation of integral of the integral for closed curves only. So if we are given integral along with complex function, along with a closed region or along with closed curve, we try to do the problem by our step-by-step procedure using the one of the theorem, Cauchy's theorem or Cauchy's integral formula only. So with this, the complex integration is completed and we stop the class here on. This is about the complex integration.